So what we need to do next is look at how we can relate the ideal gas law to stoichiometry problems. And at its essence, it's very similar to mass to moles to moles to mass problems. So let's say we have a reaction that looks like this. I have two A's make like three B's, right? And then I have grams of a substance. So this is what we've done before. You have grams of A, you'll convert it into moles of A, right? Well, to do that, you need some way to convert it, and that happens to be the molar mass of A. And normally we would say MM, like that. And then we can go to the moles of B using the mole ratio. And then moles of B, we could go to grams of B. And again, this we would use the molar mass here. So that's sort of the standard conversion if you have mass and you want to go over to moles, for example, or grams, for example. But if you have mass of A and you want to go to moles of B, you would just stop when you would get, for example, like to this point here. You don't need to do that step once you get to those units. Now, how is a gas law problem different? Well, it's really not different. It's just adding another route to the moles. So to get to A, remember you have four variables. You have pressure, volume, temperature, and the moles is up here in this part of the equation. And what you need is the ideal gas law. PV is equal to nRT. So if you're given pressure, volume, and temperature, you can use the ideal gas law to go to moles of A and then to moles of B. And from there, you could either go to, use an ideal gas law to get to pressure, volume, or temperature, or you could go, for example, using the molar mass to grams of a substance. Okay, so let's go ahead and look at a problem, and we'll see how that lays out. So here's a problem where I have two H2O liquid go to form two hydrogen gases and an oxygen gas. And the question is saying calculate the water mass needed to produce 1.42 liters of oxygen at 375 degrees Celsius and 3.5 atmospheres. Now, the red flag that this is a gas stoichiometry problem, again, is the fact that you're given 1.42 liters. Your liters, you have that's a volume, right? You have a pressure and you have a temperature. So the way we're going to do this problem is we're going to use ideal gas law. And we're going to get to moles of A. Or moles, of oxygen, like this, right? Once you have the moles of oxygen, you can go to the moles of water using the mole ratio, and then from there you can go to grams. So the pathway will be P, V, and T to get to moles of oxygen, and then we're going to go to moles of water, the thing that we're looking for, right? So we're given oxygen, we're looking for water. And then once we have water, there's a lot of different ways we could go, but we want mass. So we're going to go to mass of H2O like that. And so this is the mole ratio. Let's call it mole rat. And this one is the molar mass of water. And this is the ideal gas law. So what I want you to do is go ahead and set up and calculate for the moles of oxygen. And when you go ahead and pause the video, and I'll figure that part out on the slide. And when you come back, we'll go over it. So here's a calculation for the moles of oxygen. Again, like I usually do, I write all my variables down one side. I write the values I'm given, right? And then I make sure that each one of these units matches the units that are in R. So they match the units that are in R. And then I go ahead and rearrange my equation. So my equation was the same one that we've used before. It's N is equal to PV over RT. And then I go ahead and I plug the atmospheres, the liters, and the temperature had to be converted over to Kelvin, and the value for R in the units. And I double check to make sure I did it right by canceling all the units. If there are units that don't match, you can't cancel them. That means you have to change something, okay? And then this is the number of moles of oxygen that I got. Now it's like a stoichiometry problem where you're going from moles of one substance to grams of another. And so we'll go ahead and do that part together. I need grams of H2O. So I'm going to start with my moles of oxygen. And to be clear, where I'm at in sort of what we're doing is I need to go to moles of water. So there's 2 moles of H2O for every 1 mole of oxygen. And then the molar mass of water is 18, oops, sorry. I got it. Yep, that's 3.435. Sorry, I should have paused that. That's what I do in the background when I'm pausing all the time. Grams of, and this is actually supposed to be H2O like that. So we have 3 significant figures in our problem, so that should be 3.44 grams. Okay, so in this example, what you need to do is work on this problem. Let me set it up for you, and then I'll pause it, and then you can work it out, and then you can check your answer, and we'll go through it. Okay, so let me set this up for you. It says what volume of oxygen in liters measured at 782 millimeters of mercury and 25 degrees Celsius completely reacts with 53.2 grams of aluminum. And as we often say in these problems, right, start with whatever you can calculate the moles of. So we're going to react with aluminum. So I have grams of aluminum here. And then I need to find the volume of oxygen gas, right? So I'm going to go to grams of aluminum, and then I have a balanced equation. So hopefully this makes sense. We're going to do moles of aluminum. And then from that and the balanced equation, we'll go to moles of oxygen. Now, since we need to find the volume in liters, and we're given a pressure and a temperature, and then we're going to calculate the moles, we should be able to calculate the volume, right? So from that, we're going to go to volume of O2 using the ideal gas law. So this will be PV equals nRT. This is molar mass, and this will be your mole ratio. Okay, so go ahead and give that problem a try, and when you start up, I'll go over the answer with you. Okay, so here's the solution to the problem. First thing I did was actually pressure. I converted that over to atmospheres. The volume's what I'm looking for. Moles, which will be the moles of oxygen, is what I need. I start with the 53.2 grams of aluminum, converted it to moles using molar mass, used the mole ratio to get to moles of oxygen, so it's about 1.5, roughly 1.479. And my temperature was 298 Kelvin, and then I just plugged it all into the equation, solved for V, and then plugged all the values in. I got 35.2 liters of oxygen gas produced under those conditions. Again, this is like all the other problems that we've been doing, really. P, V, N, and T, you lay them out, you look for the values you have, and you look for the values you're looking for, really. And then you figure out how to convert things to the units you want. So if you have grams, you're going to need moles. In this case, the mole conversion was a little more complicated because we needed to do the stoichiometry of the reaction first. But the pressure conversion was the same as ones we've done before. The temperature is the same as what we've done before. And then plugging things in. And all you have to really do to sort of finish this off, if you want to, you just double check that all the units cancel out. Atmospheres will go like this, and Kelvin will go like that, and then you'll be left with liters, which is what we have down here.